Swayam Prabha. Digital India. Educated India.
Good morning, welcome back. So, today let us start with discussion on self inductance, define the self inductance and mutual inductance of a magnetic circuit. We already have their definition, it is not like we do not have their definition, but what we want to sort of do is dive a bit deeper into it and connect it with the geometry of a circuit, so that we get a method to calculate the self inductance. So, towards that end, let me again take a simple geometry. Something like this. And let me duplicate it a bit. Okay, in this geometry again, this is a iron core and I have a winding like this, and this coil has n number of turns, and I may have connected it through a battery or some such a switch and connected a current which will flow through this. So, again using the right handed screw rule, we know that this will set up a flux lines which will follow a path like this, and then we let us say that this has a area of cross section A in meter square, and now we know that this plus minus E, the way we have defined our convention of V and E. So, this will be plus d psi by dt, where psi is the flux linkage which is n times the phi. So, the n times of phi is the flux linkage. So, you will get it as n d phi by dt, and so let's look at this lambda itself. First of all, the flux linkage, which is n times of phi, which is nothing but n times of b times of area, b times the area of cross section, which is again can be written as n times mu 0 mu r h times of A, substituting for B, which can be written now as rearranging mu 0 mu r n A and then the H, which I can write as, if the current entering is I, then it is Ni by L by the definition of H, where the L is this length of the complete mean trajectory which is shown here. So, therefore, I can further write this as mu 0 mu r n square A by L times of I, and again the strictly speaking flux linkage unit is Webers only, but because it is multiplied, we multiply number of turns times flux to, so to indicate it in our writing, we prefer to write it as Weber turns. Now, if you look at this just depends upon the magnetic material, number of turns of the coil and the geometry. The A by L ratio depends upon the geometry. So, this whole thing can be called as a permeance P, which is a constant, and where the permeance P is n square A by L, and so the permeance is this can be written as n square mu 0 mu r A by L times of I, and this only depends upon the geometry of the magnetic circuit, nothing to do with the coil. The coil could have coil has n number of turns, it could have 2n number of turns also, it is okay. So, this is n square of permeance. This is what I call as the permeance of the magnetic circuit, which is mu 0 mu r A by L times of I, and so lambda, which is given by this value, lambda which is given by this flux linkage, so many Weber turns, and the ratio of lambda by I is a constant, is it not? The ratio of lambda by I is a constant, and this is called the inductance of the coil, the inductance of the coil. This is the inductance which is associated with the coil. It is not the inductance of a magnetic circuit, it is the inductance of a coil, because the number of turns also come into picture. And this is also, if you look at the reluctance that we had written earlier in the last lecture. So, this is basically 1 by reluctance of the machine. So, therefore, why? Because the reluctance is 1 by mu 0 mu r L by A. So, therefore, the self inductance or inductance of a coil having a reluctance R and number of turns N is given by N square by R, the unit being Henry. Now, let us look at if you had mutual inductance. Actually, lot of times we have to deal with mutual inductance, and in that sense let us think of two coupled coils. Just for the sake of discussion, I am taking a circular ring or a toroid kind of a thing and housing two coils on it. So, let us say this is one coil and let us say this is the other coil. Okay. Now, again the mean path I am going to take is for flux path. For that I am going to take a geometry like this, and if this is a ferrite core, then this is let us say coil 1, this is let us say coil 2, and let us say this is the current I1 which is going to enter this coil, this is the current I2 which is going to enter this coil. Now, I will be associating, now let us look at the flux which is produced in the coil 1, flux which is linking the coil 1, flux so flux linking the coil 1, phi 1 is caused by two things, the current in the coil 1 and the current in the coil 2. So, therefore, I am going to write this first component as phi 1 1, where this is the effect and this is the cause, plus the current which is the second coil is also a cause, because it is also carrying a current and it is producing a flux. In fact, this direction is straightforward, right. First direction is that if the current is entering this, then as per right handed screw rule we know that the flux will be produced in this direction. But in the second case also, the way I have defined it, you can see that if I rotate the right handed screw in the direction from in the way the current is going, it will also create the flux in the same direction. So, both of them in this case have a additive effect, both of them are having a additive effect, and the flux which is linked, the flux which is if the currents entering are such that they create additive effect, additive kind of flux, then I am going to associate two dots here which indicate that if the currents enters these two dots, then the flux which is produced inside the coil is additive in nature. That means the coil also produces the way the coil ways, let us say the coil 1 produces its flux, the current if it is entering the coil 2, it also produces the flux in the same way. Similarly, if the current is entering the coil 2 which is I2, then the way it creates the flux, and now suppose the current is also entering the coil 1, then the way in which it will create the flux, the mutual flux, the flux which is linking both the coils, that again is in a additive way. So, you in this case I will write this as, so the dot convention is very important when dealing with mutually coupled coils, and in this particular case I have taken a perfect coupling. For the time being I have taken a perfect coupling, which is to say that I have ignored or I have said that there is no leakage flux from either coil is what is what the main thing that I am saying here. In this case there is no air gap, so no need to worry about fringing. So, no need to worry about fringing. So then the phi 1 will be, I can write phi 1 as the self inductance of the coil 1, but I am going to use for the time being L11, you can even call it just L1 also, times I1, the current which is flowing through it, and no, I am sorry, I made a mistake. Where before we bring in flux inductance into picture, the flux story has to be converted into flux linkages, because inductance is always defined as the ratio of the flux linkage to the current which is the cause of it. So, the flux linkage is what is important. So, therefore, let me first write the phi 2 also. Similarly, phi 2 can be written as the flux linking the coil 2 due to current in the coil 2 and flux linking the coil 2 due to current in the coil 1, and again additive in nature. So this is fine. So this is what I have got. Now let us convert this flux story into flux linkage story. So the flux linking the coil 1 will be N1 phi 1, which will be N1 phi 1 1 plus N1 phi 1 2, and the flux linking the coil 2 will be N2 phi 2, which will be N2 times phi 2 2 plus N2 times of phi 2 1. Now we need to define self inductance. We have already defined, but at that point of time we had only one coil and a magnetic circuit. In this particular case, so I will specialize my definition like this, that self inductance of the coil 1, which is L1, or if you want you can also call it as L11, is equal to N1 phi 1 by current I1 when I set I2 to 0. That means the coil 2 is open circuited, there is only, so if this coil is open circuited, it cannot create any magnetic flux. If it cannot create any magnetic flux, it does not have any, no interplay comes into picture. So there is a basically back to the basic simple thing that I have a coil and a magnetic circuit, and it creates, when I push current through that coil, then it will create a flux in the coil, and the ratio of the flux linkage, which is the number of turns of that coil times the flux that it has created, which is linking itself, that same coil, divided by the current which is flowing through it, is the self linkage. And we have already seen that this can be written as N square by R, where R is the reluctance associated with this magnetic geometry, So and the unit is of course Henry. So there is another self inductance in this case. There are two coils on this magnetic structure. So there is another one which is L2, or if you want you can also call it as L22, which is same as, which will be defined as N2 phi 2 by I2 when I open circuit the first coil, and this will be similarly, we have already done this derivation. So this will be similarly N2 square by R Henry. Now in this example that I am working with you, both of them share the same geometry. So the reluctance which is associated with the geometry of this magnetic structure is the same in this and same in this particular case also. So therefore there is no issue nothing to sort of worry about, and I am going to use the same reluctance in both of these. Now let us come to what is a mutual inductance. So I will define two mutual inductances, one M12 and another M21. M12, the mutual inductance M12 is the flux linking the coil 1, flux linkages. So due to flux linkages associated with the coil 1, due to current flowing only in the coil 2. So what we have done is open circuited the coil 1. So, I1 is set to 0, cause is coil 2. So, a current I2 is flowing through the coil 2. What does it do? It produces a flux phi12, and that in this example of perfect coupling, the same flux phi12 will link both these coils. So, therefore, the phi12 is produced by this coil and it goes and completely goes and links the coil 1. So, the flux which is linking it is phi12, but that flux is amplified by the number of turns N1 in this particular case. That is that is because why does this flux linkage and flux, they get a their ratio, if you take, then it is the number of turns. That comes from the fact that the induced EMF as per Faraday's law we have seen is n times of d phi by dt, and if you take that n inside, then the number of turns, basically the EMF gets a multiplication factor of n due to replication of that single coil structure n number of times. And so, we take it inside and assume as if there is one turn, but the flux has becomes n times. So it instead of it just another way of putting the same fact, that is one turn flux becoming n times, or n turns but flux not becoming n times, but flux remaining the same. As far as induced EMF is concerned, it is one and the same. So, therefore, and practically everywhere we need to worry about the EMFs and the currents. So, M12 in this case is going to be N1, the flux current flowing through the coil 2, cause is the current in the coil 2, creates a flux phi12 which is linked with the coil 1, amplified by N1 the number of turns on the coil 1, and this is to be divided by the cause, which is the I2 current in the coil 2. So, other way of saying is, let there be a unit current, 1 ampere current flowing through the coil 2, injected in the coil 2, put a flux meter and measure what is the flux associated with the coil 1, some way measure that flux which is associated with the coil 1. Then once you have got that phi12, which is the flux which is linking the coil 1, then just multiply it with the number of turns of the coil 1, and that gives you the mutual inductance M12. So, now in this case, what is phi12? Phi12 is going to be B times, let me do it below. This is phi12 is going to be B times A, where B12, if you want, you can write it as B12 times of A, which is same as saying that B can be written as mu 0 mu r times H. Actually, I can just write this as B2, that is the flux created in our case, the flux created flux density which is created due to the current in the coil 2. So, I can write this as N1A mu 0 mu r H2, which can be written as, why am I using this 2 subscript? Because the cause is coil 2, and so H2 is actually the MMF which is associated due to current in the coil 2, which is in our case N2I2 by L, and so and this whole thing has to be again divided by I2. So, this whole thing again has to be divided by I2, and then this thing also has to be divided by I2. Why did I divide it by I2? Because this is only representing the numerator. I had not put this division by I2 here. So, now I have just added that division by I2 here. So, the I2 and I am sorry. So, the I2 and I2 this will cancel out, and what do you get? N1 N2 mu 0 mu r A by L. But what is this? What is this? This is the permeance. This is the permeance associated with this magnetic structure, which is N1 N2 rho, which is also same as N1 N2 by the reluctance of this circuit, and again the unit is H. So, therefore, M12 is M1 N2 N1 N2 by the reluctance of the circuit, and therefore, it is very obvious that if you interchange in this particular case, if you want to calculate M21, you should just interchange in this particular case the subscripts 1 and 2. The reluctance is the same either way, so it does not matter. So, therefore, in this case also we also get this to be M21 is equal to, this symmetry will be there, this symmetry will be always there. M12 and M21 will be equal to N1 N2 by the reluctance H. So, now compare this with L11 or L1, which was N1 square by R, L22 which was N2 square by R. So, two things come to our notice in this simple geometry. The reluctance is the same in the denominator, the reluctance is the same, but the self inductance is proportional to the square of the number of turns of the coil itself. It has nothing to do with what are the number of turns on the second coil, and so therefore, L22 is only proportional to N2 square, but the mutual inductance, as the word implies, both the coils will also play a role in it, and so the mutual inductance is proportional to both N1 and N2 and is reciprocal by the reluctance. So, in some sense, because you have a N1 N2 and N1 square, both of them basically are quadratic terms in the number of turns, that part of it is still shared between the two, and there is a symmetricity which is M12 equal to M21. The last interesting thing is, if you take L11 into L22, what does that become? N1 square N2 square by R square, which is same as N1 N2 by R whole square, which is equal to, now I will just write this as M square. So, I will just write this as product of L1 L2, and because they are symmetric, I am going to just use one mutual inductance M. In case of two coils, this is good enough, L1, L2 and M. This is absolutely good enough thing to do. When you have multiple number of coils, the 3, 4, 5 like that, and they are mutually coupled with each other, then of course we need to be a bit more bit more careful about it. So, M therefore is what? Square root of under root of L1 L2. So, take the self inductance of the coil 1, take the self inductance of the coil 2, multiply them, square the square root, and that is the mutual inductance of a perfectly coupled system. But if, as in reality, it will happen, suppose some flux leaks here and the some flux leaks here, if this is the way the flux two fluxes leak in this particular coil, then this flux which is leaking, okay, this flux which is leaking here will never go and link the coil to. Similarly, the flux which is leaking here will never go and link the coil 1. So, therefore, empirically we know that the mutual coupling will be a bit lower. So, what we will do is, in such a case we will say that mutual coupling is given by M, which is equal to some k times under root of L1 L2. K is called the coupling coefficient, and therefore K is less than or equal to 1. In the perfect geometry, no leakage and all, K is 1, otherwise K could be 0.9, 0.8. The suppose just for example, think of it that this was just a tube with air inside, not a magnetic structure at all. Then the coupling coefficient would be very small. Even then, because whatever will get linked in that case will be due to only a leakage from here to here. But whatever is this green path which we have shown here, instead of that, now think of this as a leakage flux only. So, leakage flux will keep reducing, as I keep going away and away. So, therefore, if this was just two coils on a toroidal structure, but air inside and nothing more than that, a coupling coefficient may be just 0.1, 0.05, it would be very less value. So, the role of the magnetic material, is actually to increase the coupling coefficient to a value which is closer to unity. Okay. Now let us look at this dot convention a bit more carefully. So, first of all, what was the point that I had mentioned? I had mentioned the point that a point that I had mentioned was that currents entering the dotted terminals of two mutually coupled coils, mutually coupling is coils, the coupling is of course magnetic that we are talking of here, produce additive fluxes. So, this is the way basically dots are defined. First, let us say for example, in this particular case, first what I do is I just put one dot here, push the current in this coil, that is all, and see that okay, this is creating a flux in this particular direction. Now, let us say that I decide to push the current here from this direction inside, and I find that this is the way the current is flowing. So, I rotate the right handed screw and I see that the current is becoming additive. So, therefore, the fluxes are becoming additive. So, immediately what do? I say okay, then my dot should come here only. But now let us say that for the sake of discussion, I take one more coil like this and orient it, so I take a coil like this, it goes from below, comes back from above, then goes back from below, comes back from above like this. It's just become exactly the same orientation. So that's not what I wanted. I'm sorry. Just let me edit it again. It goes back from below like this, comes from above like this, goes back from below and comes back like this, and then again goes back from below, comes back like this. Now let's say this is my coil number 3. Suppose that I put the current here, I push the current here. Then what will happen when I move the right handed screw? You can now see that the right handed screw is no more moving in the clockwise direction like what it was doing here. It is no more moving in the clockwise direction. So now the current is going from here and I move the right handed screw, then this current entering was creating a flux which was clockwise. Now this current is creating a flux which is anti-clockwise. So they are in opposition to each other. So the dots cannot come in this particular way. So the point is, however, if I push the current from this end, the other end now, and now rotate the right handed screw, then you can see that again it is going to create a flux in the clockwise direction. So it is going to be additive. So I will go and put a dot which is going to be here. So now coil 3, coil 1 and coil 3 produce additive nature fluxes, mutual fluxes and and their own individual fluxes if the currents enter the dotted terminal. Why do we put dot? Why is dot convention so important? Because you see, after all, finally whenever you buy a device or a gadget, whether it is a transformer or any other mutually coupled circuit, to figure out what is happening inside, will you like open and see the way the coils have been wound, what is the orientation? No, instead of that, even though it is put up as a black box, all the manufacturer or the person who is doing the tests for putting the dots has to do is do this check once, put the dots appropriately at the outside terminals, and then the end user can just simply use it without trying to understand the geometry and the way orientation or the direction in which the way winding has been wound. So let's say now that I have two mutually coupled coils like this, okay. Their self inductance is L1, L2, and their dots are as shown here, and I join them like this and then connect with then let's say connect it with a battery. I connect them with a battery. So my question to you is, what is the net inductance of this coil? That is it simply L1 plus L2? It should not be, right. I mean if L1 and L2 do not have any mutual coupling, then the series inductance, net series inductance of the coil will be L1 plus L2. But the moment there is a mutual coupling between the two, then the net inductance, because of the effect of mutual inductance, will change. Now, let us see how it changes. So, if this is V and if the voltage drop here is plus minus V1 and let us say this voltage drop is plus minus V2, then I can write V to be equal to V1 plus V2. Now, let us write for what is V1. So, V1 first of all will be the voltage which is created due to voltage which is induced in the coil 1 due to its own current, which we know is the L di by dt or L1 di 1 by dt. But then there is also you see V1 is basically d psi 1 by dt, is it not? But what is d psi 1? It has two components, psi 1 1 and psi 1 2. That is the flux linkage that is induced in it due to its own current, and the flux linkage which is induced in it due to current in the coil 2. And so, this is L1 I1 and this is M12 I2. So, therefore, this is going to be equal to L1 di1 by dt plus M12 di2 by dt. So, this will be V1. Similarly, V2 will be L2 di2 by dt, and since there are only two coils, I will just go by M di by dt, and this will be M di1 by dt. So now what I am going to do here for this V1, I will substitute this. So, I will get L1 di1 by dt plus M di2 by dt, and for V2 what should I substitute? I should substitute this. So, I will get plus M di1 by dt plus L2 di2 by dt. But then you can also notice one more thing, which is that I1 is equal to I2 is equal to I, because the two coils are connected in series. And what role has the dot convention played? What role has the dot convention played? Because the fluxes which are created by them are additive in nature. So, the induced voltages also have come out to be induced voltages also have come in V1. If you look at this particular frame here, V1 which is L11 di2 by d2 plus M di2 by d2. So, it has come with a plus sign here. Similarly, in this its own voltage drop for V2, if you look at for V2 its own voltage drop, which is L2 di2 by dt, has been further augmented by M di1 by dt. Again it has come with a positive sign, and now I1 is equal to I2 is equal to I. So, therefore, this becomes equal to L1 plus L2 plus 2M di by dt which basically means that the equivalent L, this is the L, if you write this as L equivalent di by dt is equal to V, then this implies that L equivalent is L1 plus L2 plus 2m, correct. Now, again to grasp this more clearly, let me alter the way these circuits are connected as follows. The dots are here and the battery is here. The current which is flowing through them is still I, that is I1 is equal to I2 is equal to I. Now, you look at it carefully. What happens to lambda 1? This is coil 1, this is coil 2. What happens to lambda 1? Lambda 1 will be phi 1 1, and because the current is exiting the other dotted terminal, this current is, this phi 1 1 is the one which is created by its own current, and it sets its own direction, which is phi 1 1. But because this current is exiting, the current I is exiting the other dotted terminal, actually it will create a subtractive flux, it will create a subtractive flux which will be with respect to phi 1 1. So, therefore, when we write this V, for the time being let us not have a resistance here, so that we can just write this V equal to, this is plus minus V1 and this is still plus minus V2, then it is V1 plus V2, the way I have defined my plus minus conventions and the current convention. Now, this will be L di 1 by dt. Now, I will just write, there is only one current, so I will directly write L di by dt, but because the other coil, the current which is not entering in the other coil, because the current is not entering the dotted terminal, but rather leaving the dotted terminal, the induced voltage will be now written as minus m di by dt. Where is this induced voltage? It is in the coil 1. What is the cause? The current in the coil 2. What is the current in the coil 2? It is I. Is it entering the dotted terminal of the coil 2? No, it is leaving the dotted terminal of the coil 2. Therefore, instead of plus m di by dt, it has become minus m di by dt. And similarly, for the other coil, V2 will be equal to N2 di2 by dt. Now, look at this. This, when I write L2 di by dt, see, when let us look at a simple circuit like this, okay, L, this is current, this is plus minus V, this is I. Now V is equal to L di by dt, this does not require, this has nothing to do with where I place dots. The voltage which is induced in this coil only requires this much of notations. This is I. If this is the way I have written it, V, then I will write V equal to L di by dt. Suppose this is I, but I put plus and minus here and then write it in my convention, then I will have to write it as minus L di by dt. Usually this is the convention that we will keep getting, unless it is a complex network in which we have arbitrarily mark currents and voltages, then we will have to be careful, but otherwise this is what we will normally end up doing. This is basically the voltages connecting the self inductances. It does not require any dots, and it always comes with the, it tends to usually come with the plus sign. So that is why I am saying here that first component of the V2 will be simply L2 di2 by dt minus, now because one current enters the dotted terminal and other leaves the dotted terminal, again I get a minus m di1 by dt, but I1 is equal to I2 equal to I. So, I will get this, which means V of t will be L1 plus L2 minus 2m di by dt. So, therefore, in a two series connected mutually coupled coils, the L inductance will be usually L1 plus L2 plus minus 2m henries. Is that clear? Okay. One last example on mutual coupled coils I will take, and then we will stop this lecture here. So, let me take one example on mutual coupled, slightly more complicated geometry. I have 3 coils here on this magnetic structure, and I have their linkages the way I shown it to you. I have put these three red dots. They are all, if the currents enter these 3 coils in the way I have shown here, then they will, if the currents enter, see these and 2 are very similarly exactly similarly wound. So, these 2 dots come here, these 2 dots also come in the same way. So, all the, so what I mean to say is this, how this coil is magnetically coupled with respect to other coils is seen here. Okay. Now, if you look at this coil, how it is magnetically coupled with one, and this is also seen here, and similarly this coil is also defined properly. So, you can think about the, very carefully go through all these dots which I have put it, and now what I have done is I have shown that this current is I1 is entering here, I2 current goes here, and I3 current is, this is the way actual currents are. Now, if you write the equation for the total flux linkages for coil 1, 2 and 3, then lambda 1 will be lambda 11 plus lambda 12 plus lambda 13. The effect is always in the coil 1. The cause here is current in coil 1, cause here is current in coil 2, cause here is current in coil 3. Similarly for lambda 2, similarly for lambda 3. Now, I am going to simply, let us say that I1 bar, I2 bar and I3 under bar, I mean it's below it, these 3 are the currents which are assumed to be entering the respective dotted terminals. Then, and this is the corresponding flux linkages which are also shown with lambda 1 under bar, lambda 2 under bar and so on. Then this lambda 1 will be L1 times of I1 bar plus M12 times of I2 under bar plus M13 times of I3 under bar and so on. Similarly for this and similarly for this. But now how is the currents flowing actually? In the first coil, actually the current is entering the dotted terminal. So, I1 bar is equal to I2. What about the second coil? In the second coil, actually the current is leaving the dotted terminal. So, therefore, I2 under bar is equal to minus of I2, and in the third coil, actually the current I3 is entering the dotted terminal. So, I3 bar is equal to I3. What about these flux linkages? Again, lambda 1 bar will be equal to lambda 1, lambda 2 bar is actually minus of lambda 2. Why? Because if the current was in the opposite way, then the natural flux orientation is also in the opposite way. So, therefore, lambda 2 bar is equal to minus lambda 2 and lambda 3 is simply equal to lambda 3. So, now I substitute for these here and I substitute for these here. Now, what I do is I see, okay, this current is minus I2, but actually I want I2 only to come in here. So, this current always multiplies the second column of the matrix here. So, this term is going to be, when you open it up, this term is going to be equal to M12 into minus I2. So, I take this minus here and keep I2 here. This term is going to be minus L2 into minus I2. So, I bring in the minus here and keep the I2 term outside here. Similarly, this will be M32 into I3. So, therefore, I am going M32 into minus of I2. So, therefore, I am going to take the minus sign here, so that this one is always now replaced by I2. So, in other words, if in the second current second variable I am getting minus I2, rather change the sign of the second column and keep I2 outside. So, I get something, I will get a structure like this. Now, what do? I look at the left hand side and I see, oh God, there is still a minus lambda 2 sitting here. So, what should I do? I should divide this row equation, which is minus lambda 2 equal to M21 I1 minus L2 I2 plus M23 I3 by minus 1. So, if I divide this by minus 1, then what will happen? This will become lambda 2, this will undergo a sign change, will become minus of M21, but because M12 and M21 are same, so I get this as minus M12, I get this as plus L2, and then I will get this as minus M23, and then the third equation I just write M31, which is same as M13, M32 which is same as M23, but again comes with a minus sign, nothing to be done here. So, this becomes the inductance matrix, and so for many mutually coupled coils, you can write basically a matrix equation of the form lambda equal to L times of I. In this case, it is a 3 by 1 matrix, 3 by 3 and 3 by 1 matrix. And very important to see that this matrix, this inductance matrix turns out to be symmetric. So, I think that is enough for the day. Let us take a break here. Thank you.